We're going to look at infrared spectroscopy. In the exam, you mainly look at how to interpret the spectra, and you don't really need to explain how the spectrometer works, but it's useful to understand how it works and how the absorption peaks are produced. In the exam, they expect you to remember some of the uses of infrared spectroscopy, and finally, you need to know the relationship between infrared absorption and global warming and greenhouse gases. As we know, covalent molecules consist of atoms that are covalently bonded together. These covalent bonds are not static, they actually vibrate, and they also vibrate more if they absorb the right frequencies, and they absorb the frequencies at which they would resonate. And those frequencies tend to be in the infrared region of the electromagnetic spectrum. Now, you don't need to explain this for the exam for A level, but covalent molecules tend to absorb infrared if the vibrations cause a change in their overall dipole. So with water, we have a molecule which has an overall dipole. It is a polar molecule. The bonds in water can vibrate in different ways. They can vibrate by stretching along the bonds, and there are different types of stretches. They can stretch symmetrically, so the bonds stretch and then return, or they can stretch asymmetrically, so alternate bonds stretch and then return to their original position. Some of these bond stretches causes a change in the dipole of the molecule, and some of the bond stretches don't cause any change. And the ones that do cause changes in the dipoles of the molecules will absorb infrared radiation. The bonds in water don't just stretch, they can also bend. The bond bending in water can also cause a change in the overall dipole, so therefore will absorb infrared radiation. Other covalent molecules with different modes of vibrations that cause a change in dipole will also absorb infrared radiation, and some of the molecules don't have vibrations that cause changes in their dipoles, so they are infrared inactive. Different types of bonds and different vibrations will absorb at different wavelengths or different frequencies of infrared, and we can measure those infrared absorptions using an infrared spectrometer. And this is a simple explanation how an infrared spectrometer works. So you have a sample of your unknown compound, and we've chosen an organic compound because they are covalent compounds. And then we shine through different wavelengths of light through the sample. Some of the frequencies of the infrared will be absorbed by some of the bond vibrations or the different types of bonds in the organic compound. Any infrared that's not absorbed will be transmitted to a detector. The signal from the detector will be interpreted by a computer. That can be plotted out and analysed by a human being, or sometimes the computer itself can match the spectra with spectra of known compounds in the database it stores. Now, you don't need to explain anything in the exam about how those absorptions are caused. So you don't need to explain anything about dipoles. You don't even need to explain anything about vibrations or bonds. All you're going to do is interpret infrared spectra and look at what absorptions are present in these spectra, and then interpret those absorptions and have a guess at what bonds are present in the sample. You'll see real examples of infrared spectra in your classwork booklet, and you're going to work through these using the datasheet from the exam board. I'm going to first of all talk about what the axes mean, and then how to interpret the infrared spectra using the datasheet. On an infrared spectrum, you see axes of absorption and wave number. The y-axis can also be labelled transmission, so the bottom can be 0% and the top can be 100% transmission. So this means that there's no light being absorbed if there's 100%, and there's light being absorbed here to cause this trough, which you actually call a peak. If the axis is labelled absorption, then the bottom here will be 100% and this will be 0%. So we have 0% here and then 100% here, and this will be percentage. The x-axis, as we said, is wave number. So the wave number relates to the wavelength or the frequency of the infrared light that goes through the sample. Chemists use wave number rather than wavelength or frequency because the values of frequency are very, very high. I think they're in the terahertz, and the wave numbers are very, very small, and I think they're in microns and micrometers, so 10 to minus 6. So chemists tend to use instead wave number, which is really the inverse of the wavelength, in centimeters. As you probably know, the equation for the relationship between frequency and wavelength for electromagnetic waves is frequency equals the speed of light divided by the wavelength. And the units therefore will be in meters for wavelength if the speed of light is in meters per second. So the wave number is the inverse of the wavelength in centimeters rather than in meters. And this gives us numbers which are easier to write because they'll be in the thousands rather than in 10 to minus 6. One thing you've got to be aware of about the wave number axis is that the scale goes downwards from high number to low number, and that relates to the fact that as you're going from left to right, the wavelength is actually increasing and the inverse of the wavelength is going to decrease. And these troughs here, which are called peaks by the way in infrared spectra, are when the substance is absorbing the infrared. So these troughs are due to the absorption of infrared at different wave numbers or different wavelengths. So we call these absorption peaks. Although think about it, these are really troughs and this is really transmission. So 100% transmission and zero transmission, but you have to get used to the fact that these are called absorption peaks. The most common bonds you find on the exam spectra are obviously CH bonds because they would appear in all organic compounds, as all organic compounds have CH bonds. You often find OH bonds for alcohols and OH bonds for carboxylic acids. Don't worry about phenols yet, we look at those in the second year. You also find double bonds between carbon and oxygens for aldehydes, ketones and carboxylic acids. And again, these you don't have to worry about until the second year. And with the OH bonds for alcohols and carboxylic acid, you should also see the CO bonds for these. This doesn't mean you won't find any other bonds in this spectra, but these are the most common ones. To spot the difference between the OH bonds in carboxylic acids and alcohols, you need to look at the range of the wave numbers for each of these. The range of wave number for the carboxylic acid is actually lower than that for the alcohol. You can see that on the table. You also notice that the carboxylic acids are labelled broad peaks rather than not being labelled at all. You've got to be aware that before 2016, the exam board said that the OH peaks for carboxylic acids were very broad and the OH peaks for the alcohols were broad. So there are different data sheets for the past papers before 2016. So be aware of that when you do past papers and make sure you use the correct data sheet for those past papers. So if you look at the spectra here, I've got 3 spectra here with OH peaks. They're in the range around 3000. But as you can see from the data sheet here, the carboxylic acid peaks are lower in wave number than the alcohol, as we said. So if you look at the 3 peaks here, this peak here has a higher wave number. It's around 3400 compared to these peaks here. That one here and this one here are closer to 3000, about 3100. So this is likely to be the alcohol and these are likely to be the carboxylic acid peaks. Often you see that the carboxylic acid peaks, which are broad in the new specification, or very broad in the old specification, they are so broad that they cover the CH peaks. So these CH peaks you can hardly see because the broad OH peaks covering them, and you can see it here as well. And here you can't even see the CH peaks very well at all. Whereas the alcohol peaks are not as broad, they're narrower, and you can actually see the CH peaks coming through. The CH peaks on their own would be like these. Another peak you may see in spectra are carbon-oxygen double bond peaks, and these are often due to aldehydes, ketones and carboxylic acid. In the second year we see that these bonds also occur in esters, amides, acyl chlorides and acid anhydrides. So if you see a peak around 1600 or 1800 and you suspect that the compound is an aldehyde or a ketone, you will see that peak, but you won't see the peaks for the OH because aldehydes and ketones don't have OH peaks. If you see a very broad peak in the range for carboxylic acid, you should also see the peak for the C double bond O because a carboxylic acid has both a C double bond O and a OH bond. So we now know the absorption peaks are due to different types of bonds vibrating, and all you're going to do in the exam is to work out what type of bonds are present by looking at the data sheet and matching the wave numbers of the peaks with the data sheet. The number of peaks in the infrared spectrum doesn't tell you how many bonds there are. So the fact that you've got a peak for an OH bond for an alcohol doesn't mean there's only one OH bond in that molecule. There could be more than one OH bond that contribute to that peak. Something else you've got to be aware of when you're looking at infrared spectra is that the region below around 1600 per centimetre, so approximately this region here, is called the fingerprint region. The peaks in the fingerprint region are caused by multiple bonds vibrating, so you can't use that pattern in the fingerprint region to identify one particular type of bond So you can't look up the datasheet and work out exactly what that peak represents in terms of a bond. However, a computer can be programmed to match the pattern in the fingerprint region with fingerprint region patterns from spectra of known compounds. So a computer can do that very, very quickly and be able to identify the compound because the fingerprint region pattern is very specific to a particular compound. So it's like a fingerprint. In the syllabus, it tells you that you need to be aware of the uses of infrared spectroscopy in monitoring air pollution and also in its use in modern breathalyzers. So one of the uses of infrared spectroscopy is in modern breathalyzers. In the very, very early days of breathalyzers, if you were stopped by the police, you were asked to blow through a tube, and that tube used to contain potassium dichromate, which is orange. As we know from the alcohols topic, alcohols are oxidized by potassium dichromate. Potassium dichromate is an oxidizing agent. We'll look at this equation in more detail in the second year, but as the alcohol is oxidized by the dichromate changes colour to green, which is chromium 3 plus ions. The alcohol itself is oxidized to the aldehyde. The problem using dichromate as a breathalyzer is that other things can be oxidized by the dichromate, so you get false positives. Modern breathalyzers use different methods of detecting alcohol, and one way of detecting alcohol is using infrared spectroscopy. And these machines tend to be at the police station as they're larger and more accurate. So at the roadside, they do preliminary tests, and that is not sufficient evidence for a case in court. So they need to do a more accurate test at the police station using infrared spectroscopy. The infrared breathalyzer looks at the fact that the alcohol has an OH peak. Unfortunately, water in your breath will also produce an OH peak. So what they do, they look at the CH peak as well and use that to measure the concentration of the alcohol. You don't have to explain this in detail for the exam. All you need to know is that this is an application of infrared spectroscopy. Another use of infrared spectroscopy is in its use in monitoring air pollution. So this can be roadside air pollution and also directly measuring the exhaust gases coming out of your car. So if you take your car to the MOT test, they will pass the exhaust gases into a spectrometer, so that's likely to be using infrared to measure the concentration of those gases. Finally, in the syllabus, you need to be aware of the fact that infrared radiation is absorbed by some atmospheric gases that contain these bonds, which could lead to global warming, and we can explain why that happens. We mentioned earlier that some vibrations of bonds resonate at the same frequency of infrared radiation, so they absorb infrared. That absorbed infrared will cause the vibrations to increase in these molecules. Those vibrations get passed on to neighbouring molecules, even ones that don't absorb infrared. So the vibrational energy will be passed on to neighbouring molecules like nitrogen and oxygen, which is the main component of the atmosphere. So over time, the atmospheric temperature rises as these particles gain more energy. So that's why some people want to reduce the amount of carbon dioxide released from burning fossil fuels. Some people believe that replacing fossil fuels or carbon-based fuels with hydrogen fuels and moving to a hydrogen economy will reduce global warming. But water vapour is actually a very potent greenhouse gas, probably more potent than carbon dioxide. So will that really reduce global warming? Nevertheless, governments and individuals are encouraged to reduce the amount of carbon dioxide released into the atmosphere. So initiatives like taxation and grants to alter the behaviour of consumers have been introduced in many countries. And between nations, there have been agreements to set targets to reduce CO2 emissions from each country. You need to remember these two agreements for the exam as examples of international agreements. So the Kyoto Protocol was agreed in 1992, and the Paris Agreement was fairly recent and was made in 2015. This video has covered all the topics in infrared spectroscopy part of the syllabus.